Hey guys, Dibyajyoti here from The Fast Engineer, and today we are going to learn Kirchhoff's current law in just 5 minutes, in a way you will never forget. This law was given by the German physicist Gustav Kirchhoff and is one of the most important laws in electrical engineering. Now imagine a classroom. Students enter the classroom and students leave the classroom. Now think carefully. Can students suddenly disappear inside the classroom? Of course not. If 8 students entered the classroom, then the same 8 students must eventually leave. Otherwise, students would start accumulating inside the room. Electric current behaves in exactly the same way inside an electrical circuit, and that's called Kirchhoff's current law, or simply KCL. Kirchhoff's current law states that the algebraic sum of the currents entering any node is zero. In simple words, the sum of currents entering a node is equal to the sum of currents leaving the node. Now, what exactly is a node? A node is simply a junction or meeting point in an electrical circuit where two or more wires or circuit elements are connected together. Suppose at a node, currents I1 and I2 are entering the node, represented here by green arrows, whereas currents I3, I4, and I5 are leaving the node, represented by red arrows. Now listen carefully. Whatever current enters the node must leave the node. Current cannot suddenly disappear at the junction. So according to Kirchhoff's current law, I1 plus I2 equals I3 plus I4 plus I5. This simply means the sum of total incoming current is equal to the sum of total outgoing current. Now let's write this in algebraic form. We bring all the currents to one side of the equation. We get I1 plus I2 minus I3 minus I4 minus I5 equals 0. Can you see what happened here? The currents entering the node are taken as positive, and the currents leaving the node are taken as negative. That's why the algebraic sum becomes 0. So whenever you solve KCL problems, just remember one simple thing. Take entering currents as positive, leaving currents as negative. And if you add all the currents properly, the final answer will always become 0. Let's take an example to understand this better. Suppose at a node, current I1 equals 4 ampere enters the node. Current I2 equals 6 ampere also enters the node. Current I3 equals 3 ampere leaves the node. Current I4 equals 5 ampere leaves the node. Current I5 is also leaving the node, but its value is unknown, and we need to find I5. Now first think carefully. What does KCL say? Very simple. Total incoming current must always equal total outgoing current. So here incoming currents are I1 and I2. Outgoing currents are I3, I4 and I5. Therefore, I1 plus I2 equals I3 plus I4 plus I5. Now substitute the values. 4 plus 6 equals 3 plus 5 plus I5. So 4 plus 6 gives 10 and 3 plus 5 gives 8. So we get 10 equals 8 plus I5. Now subtract 8 from both sides. We get I5 equals 2 ampere. That means 2 amperes of current must leave the node to satisfy Kirchhoff's current law. And you can clearly verify it. Incoming current equals 4 plus 6 equals 10 ampere. And outgoing current equals 3 plus 5 plus 2 equals 10 ampere. So KCL is perfectly satisfied. Now one last question you might have is, why does Kirchhoff's current law always work? Why must the current entering a node always equal the current leaving the node? Well, the answer lies in the conservation of charge. We know that electric current is simply the flow of electric charges, mainly electrons. Current is defined as charge flowing per unit time. I equals Q by T. And according to the law of conservation of charge, charge can neither be created not destroyed. That means charges cannot magically appear at a junction and they also cannot suddenly disappear. So imagine this: if 5 coulombs of charge enter a node every second, then the same 5 coulombs must leave the node every second. Otherwise, charge would start accumulating at the junction, which doesn't happen in a normal electrical circuit. And that's exactly why Kirchhoff's current law always works. If you found this video helpful, make sure to subscribe to The Fast Engineer. And if you want to understand Ohm's law just as easily, watch the video appearing on your screen right now. See you in that one.